In electromagnetism, we can apply differential forms. We have in particular the four potential A mu, which is given by four components A0, A1, A2, A3. So we are in a four-dimensional space. So it's in particular it's a four-dimensional Minkowski space. We can define the one form A to be given by A mu dx mu. And we can take the exterior derivative of this form according to the definitions that we have given regarding the exterior derivative. We know that this is equal to dA mu dx nu wedge dx mu. And this can also be written like this: 1/2 dA mu dx nu wedge dx mu, and then we have plus dA nu dx mu wedge dx nu. So I'm simply using symmetry of this, and I have rewritten the expression by changing the labels of the indices. So this first index, I'm calling it mu. I'm simply taking advantage of the fact that these indices nu and mu are dummy indices. So I have relabeled them. Here this is nu, and this becomes the index mu, but we are summing over them. So this expression is equal to this one. So it's as if I have 1/2 multiplied by 2 multiplied by this. And of course, this is a trivial equality. Now I can use some properties, the property of wedge products, and I can rewrite this as minus dx mu wedge dx mu, and this can be written as 1/2 dA mu dx nu minus dA nu dx mu, and then I have dx nu wedge dx mu, like this. And I define this object here as the electromagnetic tensor F nu mu. So I start with nu and then mu. It's a definition, and we see that F nu mu in particular multiplied by this dx nu wedge dx mu, I can define it to be equal to a two form F, and this is also equal to twice the differential of A, so the exterior derivative of A. Now this relationship between F and A is very important, because at this moment, if we take the exterior derivative of F, we see that this is equal to twice the second exterior derivative of A. But we have already proved that if we take the exterior derivative of a form twice, we get 0. So the result that we get is that the exterior derivative of the electromagnetic form, or if you want the two form associated to the electromagnetic field, well, this is 0. So this is the result that we get, and we can show that this equation contains one of the Maxwell's equations. Now, let's calculate dF explicitly. This can be written as 1 over 2 factorial, because we have a 2 form, so remember that we also have this factor. Then we take the partial derivative of f nu mu with respect to x gamma, dx gamma wedge dx nu wedge dx mu, and we know that this is equal to 0. But now, if we expand this a little bit, we can write it as df23 dx1 plus df31 dx2 plus df12 dx3, and then we have dx1 wedge dx2 wedge dx3. So you can show that indeed this expression is equal to this. Remember that this should be equal to 0 by rearranging also the order in which you write these differentials. And you have to remember the fact that f nu mu is antisymmetric, so this is minus F mu nu. You can see it from the definition of F nu mu in terms of the for potential A mu. So it's a simple thing to observe. Now, we can see from here that this quantity should be equal to 0. And this is indeed one of Maxwell's equations, and I want to show you that. In particular, let's remind ourselves of this formula. F nu mu is equal to dA mu dx nu minus dA nu dx mu. And now we can define Fi0 to be equal to, by definition, the ith component of the electric field divided by the speed of light, for I equal to 1, 2, and 3. So if you set I equal to 0, it's trivial because F00 should be 0. Since F nu mu is anti-symmetric, you can also see that from here. If mu is equal to nu, you can see that these two will amount to 0. And this is also equal to dA0 dxi minus di dx0, which is equal to the gradient of a0 minus 1 over c, the derivative of the vector a with respect to time. So this vector a contains the three components a1, a2, a3, and x0 is just the speed of light multiplied by the variable that represents time in our reference system. And therefore this is equal to E divided by C. Now the other definitions are the following. So we have F23 equal to the first component of the magnetic field by definition. F31 is equal to the second component of the magnetic field by definition. F12 is equal to the third component of the magnetic field by definition. So of course F13 is equal to minus F31 and so on. Now at this point we can use these definitions to rewrite this expression here. So from what we have just defined, it's easy to see that we get dB1 dx1 plus dB2 dx2 plus dB3 dx3 equal to 0. But what is this? Well, this is exactly one of Maxwell's equations. In particular, the divergence of the magnetic field is equal to 0. So it's very simple to observe this. Then in the next video I also want to remind you how you can derive another Maxwell's equation. And in order to be able to recover all of Maxwell's equations, we have to define the so-called Hodge dual. But this will come later. We can obtain another Maxwell equation very naturally from the theory that we have developed so far. In particular, we have defined the first component of the magnetic field to be equal to F23. So remember that F represents the electromagnetic tensor, in particular F mu nu. Then we also define the two form F associated to F mu nu. And F23 gives us the first component of the magnetic field. And this is equal to dA3 dx2 minus dA2 dx3. Then we have also defined B2 to be equal to F31, which is equal to dA1 dx3 minus dA3 dx1. And finally, we have also defined B3 to be F12, and this is equal to dA2 dx1 minus dA1 dx2. So from these three components, it is easy to observe that the vector B, which contains the three components B1, B2, B3, so this is the vector associated to the magnetic field, it's just the curl of the vector A, which contains the three components A1, A2, A3. We have also found last time that The electric field divided by the speed of light can also be written as the gradient of A0 minus 1 over c, the speed of light, derivative of the vector A with respect to time. Now, if we take the curl of this second expression, we see that the curl of E divided by the speed of light is equal to the curl of this gradient, but the curl of a gradient is equal to 0. It's trivial. And then we have the curl of this expression. So we can also write it as minus 1 over c, derivative with respect to time, curl of A. But now the curl of A is equal to B, the magnetic field. So this is equal to minus 1 over c, derivative of B with respect to time. From here we get another Maxwell equation. The curl of E, the electric field, is equal to minus the derivative of the magnetic field with respect to time.